And so, on to today's lecture. Okay, so today's lecture is the 21st lecture of this course. We have only, it's 26 lectures, okay? So we're getting near the finish point, so I have to pick and choose the things that I feel would be most beneficial to you. So it's gonna be sort of an assortment of topics in machine learning. Specifically, I'm trying to pick the things that I think would be most beneficial to you guys in the future. Basically, these last couple lectures, I just want to leave you guys with sort of an idea of what exists, what a bunch of different fields exist. So today, we're going to talk about deep learning, specifically in the context of image tasks. On Thursday, my apologies. On Thursday and Tuesday of next week, I'm going to go into transformer models and LLMs, which, everything is a transformer nowadays, so I think that will be useful. Then on that Thursday, I think I'm going to go into a bunch more LLMs, and at some point, I do want to discuss reinforcement learning. So I'm either going to do that on next week, Thursday, or the Tuesday after next. And again, I'm not doing these fields at all justice. Each of these things, for instance, machine learning for vision has a whole, is a whole field. Colleges have whole departments dedicated to vision tasks. Same thing with reinforcement learning. Could anyone tell me the best university, like the top university program in reinforcement learning? University of Alberta. Yeah, I always find that they have one of the best reinforcement learning programs. And so I always find that interesting, especially when you don't think about Canadian schools all that much. But, Waterloo, Alberta, these places are on par with the best of the US schools. Anyway, so I do want to get into that. So I think it's good that we're going to discuss image tasks today, especially since one of the project topics are on image tasks. Then I know the natural language project. I'm going to sort of briefly touch upon it next week when we discuss transformers, because transformers are basically all about natural language processing. And again, either Thursday of next week or the Tuesday following, I'm going to touch upon reinforcement learning, because that could be helpful for the markets task. The markets topic is very open-ended. I will tell you that if you want to get into financial engineering, there's no sort of one financial machine learning thing. There's no sort of one transformer model for financial engineering. There's a bunch of different things that you could do that sort of help you process market data. So a lot of it sort of relates to reinforcement learning, so that's why I'll get into it Thursday or Tuesday. So all that is a long way of saying, I'm brushing over a lot. I'm not doing justice at all to any of these fields. My only goal right now is sort of to make you guys aware enough of the different fields, aware enough of sort of some of the different languages, so you could go on and search for these things yourself, especially when you're doing their projects. Okay, so as I said, we're gonna discuss deep learning, tips and tricks, and then we're going to discuss two different image tasks, specifically semantic segmentation, which we viewed before, and object detection and measurement, which you haven't viewed before, but is going to be important for the visual project topic. Okay. Yeah. Okay. Everyone good with that plan? Okay. Yeah. And if there's something that you're really interested in and you think I should cover, please let me know. I'm happy to alter the schedule. It's not set in stone. Okay. So Deep learning tips and tricks, and there's only one thing that I wanted to get into. Um, I mean, I was planning to do multiple like little things, but I think I'll save some of the other stuff for the transformer model lectures. But the big thing I wanted to sort of discuss is this thing called batch normalization, because you'll see batch normalization layers in in pretty much most deep learning models. Most deep learning models you'll see online. So let's discuss batch learning, batch normalization. Sorry, and batch normalization really comes up from this paper, batch normalization, accelerating deep network training by reducing internal covariate shift. So I must confess that I can't give you a really good reason why this works so well. It's one of those things that you have to just try it in your own models and get it working, and then you'll see that it's really, really useful. But I'm going to try to give some justification anyway. And directly from the abstract of the paper, they talk about how training in a deep neural network is complicated by the fact that the distribution of each layer's inputs changes during training. As the parameters of the previous layers change. So this isn't something that we've seen a lot because we haven't really analyzed a lot of deep models. But you know, when you have a deep model, you have something that is, let's say, 10 layers deep, right? And it starts off random. Okay, you start off with random weights the entire way through. So what happens in that case is that as you start training, you have a particular output, you fix the output to, right? You have an output for a particular input. That's way at the beginning, okay? So what happens basically as you start training is that you have an output, it's gonna start off with the input, the input is gonna go through a bunch of weights and values and activation functions, and then you're gonna get some random garbage at the output. Then you're gonna compare that random garbage to the ground truth. You're gonna calculate the loss. Then you're going to backpropagate through the network, right? So as you backpropagate through the network, the thing is that the layers will change, the outputs of each layers will change, right? That makes sense. You're changing the weights, the outputs of each layer will change, and the distribution of these outputs will change. So why is that a bad thing? It's a bad thing because if you have a very deep network, right? If you have a very deep network, let's say the layer in the middle, layer 5, is looking at a particular set of inputs, and it's saying, okay, for this distribution of inputs, I could change my weights like so in order to get closer to the ground truth output, which is how propagation works, right? Now, the issue is that distribution of inputs at every stage changes because you're changing the weights of every layer. So you have this very complex loop that basically the distributions of each layer are changing, and the layers are changing to match those distributions. And especially the layers towards the end of the network, the distributions of their inputs of those layers are changing far, far more than the distributions of the layers towards the beginning of the network. The distribution of the inputs to each layer towards the beginning aren't changing that much because it's just the distribution of the inputs, right? The data set distribution. That's set in stone. But the distribution of the inputs of the layers towards the end of the network, that could vary greatly, right? Because depending on what the weights of the layers in the beginning of the network are, it will greatly change the distribution of their outputs. And then those outputs will propagate through, right? So this is a thing. This is a hard thing about deep learning, right? That basically you have these layers that are dependent on each other, and you have this beautiful backpropagation algorithm. But as we have seen in a couple of other cases, it's not always what it works. We have a beautiful backpropagation algorithm, and in theory, in theory, if we keep computing the gradient, and if we keep going, and if we keep computing the gradient, doing more and more in epochs, we'll get to a maximum minima, hopefully. But it might just take an unbelievably long amount of time, right? Machine learning is really not about finding a truth or anything. It's about finding something that works good enough in as little time as possible. So this is what the authors are talking about when they say that training deep neural networks is complicated by the fact that the distribution of each layer's input changes during the training as the parameters of each layer change. So the question is, what do we do about that? Oh, and I would say so the second part is this slows down learning, and as we saw that there's ways to battle against this. If you change the learning rates, I mean, you could have sort of a learning rate decay, right? We saw that, we talked about that before. You could start off with a very high learning rate and decrease the learning rate as time goes on. You could have momentum. You could all have all these gradient, you could have all these training improvements, but it doesn't change this phenomena that the authors dub internal covariate shift. This is the term that they have assigned to this phenomena. That when you're training deep models, especially the layers towards the end of the models, could be harder to train because their input distributions are less certain. Okay, internal covariate shift. Okay. So now you know if you're in a job interview and they ask about that, now you know what that means. So how do you fix this? Well, the authors of this paper proposed a very direct fix, which was simply taking a batch, right? Remember batching? We take a segment of the data and we put that segment together to calculate the gradient. Well, why don't we normalize that? Why don't we calculate the norm at each layer, right? Why don't we normalize that to be a distribution around at a mean of 0 and a standard deviation of whatever, right? So that's the idea behind batch normalization, that as much as we want, we could put these layers into our network. We could put layers into our network, and all these layers are doing is normalizing the output of layer n-1, normalizing that output of layer n-1, and then feeding that normalized input to the input of layer n. Okay? So as far as normalization goes, we touched upon normalization a couple times. When was the last time we talked about normalization? I know I said this. I know I said it maybe last week. Oh, man, I'm blanking on the topic, though. I am blanking on the topic. Oh, with the Gaussian, with the GAN models, when we were talking about the Gaussian mixture models, yeah, when we're talking about the Gaussian mixture models and basically the inputs to the discriminator. Now I remember, right? So normalization comes up in a lot. Like, it just comes up everywhere in machine learning. It comes up everywhere in science, right? Everywhere in science, like physics and stuff, we're always instructed, normalize our data, make it easier to compute, right? So that's what this is doing right here. It's easy, like all this function is doing. This is a batch normalization function, and you could think of this as a layer, right? Same way a linear layer is simply like a w times x. You could think of this as just another layer, batch normalization. And all the batch normalization is doing is it's calculating the mean, and then it's calculating the variance of the batch that you have, and then you normalize it. You normalize the data to some new value. Basically, you subtract the mean, you divide that by the variance, and you have the output, subtract the mean divided by the variance, running through that. Scale and shift. Okay. So important thing right here is that there are two learned parameters here, gamma x, which changes the stretch of the input. Basically, it changes the stretch. And beta, that just simply moves the mean around. Okay? Why is this important? Well, you want to still have a little bit of, you want to still give the networks a little bit of control over the absolute values, right? You don't want to force them, you don't want to force each layer to use the actual normalized values. You don't want to say each layer has to only operate on data that has a mean of 0 or whatever. So you want to give the model the opportunity to alter its to change its distribution, but you want to basically just normalize the distribution. So a way to look at this is just with a little bit of Python code that, for instance, if you have a particular distribution of values that are coming out of one layer, then you run the batch normalization, and it gives you a distribution that's centered around 0 and has some standard deviation that is determined by this gamma here. Okay, and this gamma is I just set it equal to 1. Okay, so that's all the batch normalization is doing. It's literally just taking inputs and just normalizing them to some more standard space, right? So why is this important? Again, because as you're training, since you have a batch normalization layer, as you're training, each layer has control and will see a more consistent input space. Okay. Yeah. So just an example of where you might see this. Why aren't you? Oh. Oops. Oh, actually, yeah. Just an example of where you might see this. There is a very famous, this is one of the OG image processing models called ResNet. It's like a default model in PyTorch that you could load. I just got a from scratch visualization from this website here. But you will see. Oh yeah. So we have convolutional nets, 2D convolution, and we have a batch normalization. We have a batch normalization layers here. And then if we go to the forward, we see that we include the batch normalization between certain layers. And I think it's block layers 1, 2, 3. Self-make layer. Oh, it's right here. And I think it's right. Why didn't I? Oh, there we go. And think it's right there, right? So what this network is all they're doing basically is that they wrote a function to make different network layers. And one thing that they're doing is basically shoving in a batch normalization layer in between every other layer. Okay? Which, it's fine. It can't hurt. It can't hurt. It's computationally relatively inexpensive. You're just adding 2 extra parameters into the model, which given your model has like millions of parameters or whatever, right? So adding a couple extra parameters for each layer isn't gonna make or break you. So you'll see this basically in a lot of different machine learning models. Specifically, this is very common in image and signal processing machine learning models, just to put the batch normalization layer in there, just to normalize things. And it'll make training, it doesn't really, I don't think I've seen anyone say it improves. Well, actually, let me go to the previous results. So the previous results of the paper here, if you look into that paper, so by the way, that's like a seminal work. So if you know the title of that work, it's an easy way to impress your interviewer. The results here is simply to show that if you do use batch normalization, they constructed a simple MNIST MNIST network, and specifically the MNIST network they constructed is like multi-layer. I mean, the ones we construct in the lectures are all like 1 or 2 layers because MNIST is simple, right? But just to prove their point, they constructed a multi-layer MNIST network, and then they tested the accuracy of the MNIST network with and without batch normalization. And you see that with batch normalization, everything is much, much, much more stable than without it. Okay? So, yeah, I don't think I mean, this is a hard thing to say. Does it improve accuracy? I mean, it's one of those things that, you know, you could get over, you could find the same accuracy, like in theory. Like if we didn't use batch normalization, then if we just trained for more epochs, we could probably match the accuracy, right? So I don't think I would say that I would be comfortable saying batch normalization improves the accuracy. Batch normalization is mainly for making your life significantly easier, making your training significantly easier. And in a way that improves accuracy because with less time, you get a more accurate result. Okay? Does that make sense? Okay. So yeah, so I mean, I know you guys, especially with the projects, are probably going to go online and look at a bunch of different models, and you're going to see this batch normalization thing in a lot of models, people just shoving it in pretty much between every layer. So I wanted to really emphasize it's not anything special. Like it's not anything too complicated. It's literally just normalizing the inputs between each layer, and it's specifically just to make training easier. And you know, I mean, given that we're all on sort of constrained resources, that's not a bad thing. Okay. Before we leave, any questions? No? Okay. So batch normalization. Okay. So next, let's look at semantic segmentation. Okay. So semantic segmentation, we brought this up in the convolutional network lecture. So what is semantic segmentation? It's simply the idea that we want to separate objects in a picture. Okay, we want to know which objects which group of pixels belong to one object and which group of pixels belong to another object. So the way to do that is really just, well, the common way to do that, I should say, is simply you have a picture that is an n by n resolution, and then you output another picture that is the same resolution. And the only difference between the two is that whereas before the input was the actual picture, the way we would see it, the output is simply each pixel in one of several categories. Okay? So we see the picture here. For instance, we see the car, and the car is like we just colored color the car-related pixels as red. And then so over here, this car is colored as red. I mean, all these cars are colored as red. And this car is colored as red. And for instance, all the green foliage, vegetation is colored as green. The buildings are colored as yellow, and so on. Okay? So this is a very useful pre-processing step for a lot of different image tasks, right? I mean, if we wanted to locate a car, all we need to do is basically run our image segmentation algorithm, and then sort of just run a simple Python script that clusters these pixels together, right? And we could get a location of a car. Okay, so yeah, so that's semantic segmentation. That's a problem, I should say. So what do we do? How do we achieve this semantic segmentation? And we need a good data set that has an input like this and has an output like this, right? Those are hard to get. A good data set, those are actually pretty hard to do because someone has to label them, but they do exist. So we need a good data set. And as far as the model is concerned, we simply use a convolutional encoder-decoder model, which is simply, we have a bunch of convolutional layers, a bunch of linear layers. It goes to a bunch of convolutional layers here, a bunch of convolutional layers. So slowly, convolutional pooling layers, convolutional pooling layers, convolutional pooling layers. So slowly we compress the image down to get only the most necessary features from that image. And then we need to reconstruct the image in the color and the classifications we want. So we go, and from the necessary features, we go and basically blow up the image. Go back to the correct resolution. Okay. Yeah. Does that make sense? We talked about this before. Convolutional network, right? Okay. So that is what segmentation is work. But this is a sort of basically a hello world version of convolutional encoder-decoder networks. There are so many optimizations you can make to this. Okay, so one of the optimizations that we can make, for instance, is the observation that we are putting a lot of pressure on preserving all the features from all the previous layers into this little space here, right? We are basically asking the model to go from an image like this, get all the information, and compress that information, and lose none of it, through multiple layers, okay? So every time you have a network that basically has to maintain information through, many layers. That's what a deep networks are. It's gonna be tough. It's gonna be tough. Basically, the network has. There's just a natural tendency to lose information every time you perform some computation, right? So if you have multiple layers and you're going through and doing an activation function, a convolutional, a pooling layer at every single, like you're doing a convolution, pooling, activation function 10, 20 times, well, this is gonna decay the information from your input, right? The further away you get from it. So how do we fix this? Well, one way is UNet. So UNet was published in 2015, 10 years ago. And the idea behind UNet is simply to allow the encoder-decoder network to retrieve information from earlier layers. Basically give shortcuts to the information between the encoder and decoder. So it specifically does that by taking, for instance, the information at layer, in this case, I guess it would be layer 3, and taking that and copying it over here to the information in the decoder at layer 3. It will be layer 5-ish here. Okay? So all we're doing here is appending the information from a later encoder layer to an earlier decoder layer. Okay? And similarly here, we append the information from an early encoder layer to a later decoder layer, right? So this whole thing is basically forms a shortcut for the early image information going to getting copied to the later decoder layers. So how does this help? Well, it helps because you have to keep the resolution sizes consistent, right? Over here, the actual resolution of these features is kind of small, so appending it to, like over here, appending it to later in the decoder doesn't make much sense because there are two different resolutions there, right? So you sort of have to you have to add this information. You have to keep the information with similar resolutions together, okay? So just for the sake of programming simplicity, that's why you get this sort of U, right? Nested U shape. But also that there is an important conceptual idea here, which is simply that the closer we are to outputting the final segmented image, the more we need the original image, right? So this is actually very well-known. This is a very well-known technique, and it was published in 2015. But I think a lot of models since then have used these basically fast-forwarding channels to help prevent the issue of catastrophic forgetting. Yeah, does that make sense? Does the intuition make sense behind it? I think I forgot to output the actual results. I should have. Oh, we could go to the actual paper. Another way to visualize this, again, we have the architecture, and all we're doing is basically taking a layer from the output of one of an encoder layer and appending it to the input of one of the the corresponding decoder layer. Okay, so you have this symmetry going on. It's kind of beautiful when you visualize it correctly. Yeah. But I just wanted to go to the actual. Where did the actual results graph go? I mean, you had cell tracking wasn't the only. I could have sworn there was maybe I'm thinking of a follow-up paper. Yeah, I'm probably thinking of a follow-up paper. Okay, anyway. So there are multiple challenges, but you can see in various different challenges the UNet performs on par or performs better than, or on par or better than a lot of other models. This is especially true with, there we go. This is especially true with the cell tracking challenge. This is literally just an image segmentation task, 4 cells. This actually, I haven't seen this in a long time. I think it's because it's become too easy for modern models. But you see that UNet achieves a significantly improved performance over other image models from that time. Okay. Yeah, makes sense? Good. So this fast forwarding will come up basically with, this will come up with transformers, which we'll discuss on Thursday. Basically, all we're trying to do is get information from earlier in the model and put it and append it to information later in the model, right? So what's this idea? I mean, this idea is very, very analogous to the idea of attention. Oops. That we will see on Thursday. Okay, so keep it in mind. Okay. So that's all I wanted to talk about for image segmentation. The harder image task is object detection. And I'm sure we've all seen these sorts of visualizations, these sorts of AI visualizations where basically we have an image or a video and the model tracks a particular object and labels it as whatever, right? So for whether you're doing a video or a single still frame image, the concept is pretty much the same. You have a RGB image, which has typically 3 channels, a height and a width, and some K annotations. And then, so we have the data set. Ideally, we have a ground truth data set that annotates this is what's called a bounding box. And the bounding box is simply a collection of coordinates, the origin coordinates, which are x-min and y-min right here. And then the stretch, I don't know what to call it, the other side of the coordinates, which is simply x max and y max. So you need 4 values really to denote this bounding box. And just for the sake of clarity, just for the sake of no, not to, for the sake of simplicity. Sorry, just for the sake of simplicity. Typically, when we define these x and y coordinates, we define them from the range of 0 to 1. And where 0 is where 0 is this little corner of the image, basically 0 height or 0 width. I mean 0x or 0 y is this little corner of the image, and 1x or 1y is this little corner of the image, right? We just normalize everything between 0 and 1. Why? I mean, and it works out pretty well because we have a nice little function that always outputs a value between 0 and 1, which is sigmoid, right? So everything works out well. So yeah. So one important thing to note is that we have an image, and the image may contain multiple annotations, right? Not necessarily a single bounding box, but it may contain multiple bounding boxes. So we have to create models that can handle multiple bounding boxes. But yeah, so we have to create models that handle multiple bounding boxes. So there are so many different models now that for this bounding box problem, but the same general ideas permeate through. Okay, so when we want to, sorry, can we move in? Yep. Yeah. So we want to actually we want to denote a bounding box. Okay. One method to be able to define multiple bounding boxes. I mean, there are multiple methods, but one of them is simply to divide up the image into a certain series of squares, a certain grid pattern. Okay. This grid pattern is going to be a lower resolution than the original image. It's going to be much lower resolution than the original image, but this grid pattern will allow us to specify, possible bounding box locations. Okay, so these little grids are what's known as anchors. Okay, these little anchors define possible bounding boxes that you could specify. Okay, and then you could adjust the location of these anchors, and you could adjust the height and width of these anchors. Okay, so what do we do with these anchors? Well, for each of these anchors, if we want to define a bounding box that is centered at this anchor, all we really need to do is define the I and j for that anchor. We know that anchor, the position of that anchor. We could adjust the center of that bounding box using a separate I and j. And then we simply denote, we need to find a way to denote the shape of the bounding box, okay? So instead of denoting basically xy to xy1 to xy2, denoting that 4 values, one way is simply that we could simply say the bounding box has a center, and then the bounding box has a particular shape and a particular aspect ratio. I shouldn't say shape. They're all rectangles, okay? But we could simplify this problem by saying the bounding box has a particular center, and the bounding box has a particular aspect ratio, okay? And we'll just predefine a bunch of aspect ratios for our own sanity, okay? So for instance, we could say that the bounding box aspect ratios are 1 to 1, 1 to 2, 3 to 1 for the width to height. So we have a bunch of different bounding boxes like so. And then we define these aspect ratios that are one of these set values. And so the height and width we could calculate using the aspect ratio and the location of the center location of the bounding box. Okay, and SK is simply the scale feature of the image. So if, for instance, we could scale a what is this? A 200 by 200 image, or 300 by 300 image down to an 8 by 8 image. Okay. So each of these little squares, again, we call them anchors because they could each define a separate bounding box. And yeah, we just really need 3 values. For each of these little anchors, we try to optimize the model so it spits out 3 values. Input a pixel location, center point at each pixel location, and the aspect ratio. Okay? So we need to discuss what makes a good or bad bounding box. Okay? How do we measure what is a good bounding box or a bad bounding box? So for instance, in the image here, cute little kid, we have the ground truth bounding box in green here. And then we have estimates that we got from the model. Okay? So for instance here, this bounding box captures part of the kitten, but not all of it. But we need an actual measure to see how good the bounding box is, because for instance, if the bounding box is gigantic, if the bounding box is the entire image, that's not what we want. If the bounding box is just a little part of the image, that's not what we want either, right? So the metric that people typically use is what's called intersection over union. Basically, we calculate the intersection of the 2 bounding boxes. Simple math. You guys, simple geometry, you could do it very easily. And then we calculate the union, the area of the 2 bounding boxes. Okay? So intersection over union is maximized when both boxes are equal, right? If both boxes are equal, their intersections are equal to their unions. Okay? And the intersection over union is minimized when, let's say, both boxes aren't overlapping at all. That's one option. We could also say that the intersection over union is minimized when one box is tiny. They are overlapping, but one box is tiny and the other box is huge. The intersection will be small and the union would be just a big box, right? So that will be very small. So that's why people use the intersection over union metric, okay? Because the extremes, you know, when you have 2 boxes that are different sizes but are overlapping, when you have 2 boxes that are not overlapping, that accounts for a small value. And when you have 2 boxes that are overlapping greatly, that counts for a large value. Okay? So nice little way to calculate how well a bounding box works. So what do we do with this intersection over union? Well, we need to be able to output a bunch of bounding boxes. So one way to output a bunch of bounding boxes is simply, you know, we could for each of those little anchors, we have a bunch of different aspect ratios. We need to still classify those boxes. So we have to have each of those anchors output a particular classification. And we have to have the bounding boxes output a set of real values corresponding to the center position and the width and height. And we could adjust it further by just having some, that makes sense. So if we look at a particular convolutional network, there we go. We have the image that goes in through a bunch of different convolutional layers. At one point we take out the classification, then we output for FPS, directions. Oh yeah, detections. So at some point we outputs for each of the different anchors. We output the values, the classification, and the different centers and widths and heights. Okay, And these centers and widths or heights are determined within relative terms to the actual anchors at these points. Okay, so each of these anchors is like a separate output. Okay, so does this allow you to output basically an infinite number of bounding boxes in an image? No, there's a finite number of bounding boxes for any model that you could output. Right, this isn't a recurrent neural network where you could just like keep like throwing out bounding boxes. I'm sure someone has tried that, but from what I could tell, there's no real mainstream model that does that basically just outputs a variable number of bounding boxes like that in a recurrent manner. All this network does is it simply says that, yeah, I'm just going to put a bunch of outputs and align them in a grid along the image. And then for each of those boxes, I'm going to output some adjustments to the center point. I'm going to output some adjustments to the width and height. I'm going to output the classification, and then I will use the normal classification. I will optimize the model for classification loss and bounding box intersection over union loss. Okay. So that's how that works. As far as training goes, again, we could use a loss function, same as before. All we need to do really is have the loss function for the actual classification loss and have a loss function for the location, the bounding box location and overlap loss. Okay. Does all that make sense? So multiple different loss functions. This formulation is, I mean, I'm going to sort of leave it to you guys because I don't want to get bogged down too much. We have a couple more slides to get through. So I'm going to leave the actual sort of analysis of this loss function to you guys. This is what's called smooth L1 loss, very popular in image processing, but there are multiple different loss functions. If you remember the L2, we discussed L2 loss when we discussed support vector machines, how to derive L2 loss with support vector machines. Like the L2 loss is simply the square of the difference between the predictive value and the true value. The L2 loss is calculated using primal optimization. I know you guys thought you wouldn't hear that again, but primal optimization was L2 loss. L1 loss is typically calculated using dual optimization. So remember, with dual optimization, the idea behind dual optimization is simply that you encode certain constraints into the loss function. And we discussed that with the general with GANs also. Okay, so you guys could explore that a bit more, or ping on Piazza if you need a bit more explanation here. Okay, so now it comes up an issue with inference, right? If we have a model that could seemingly spew out just a ton of bounding boxes, right? I mean, we could run an image through the model. We'll get a bunch of bounding boxes out. And it will give out, just for each anchor, it will give out lots of bounding boxes, okay? So how do we get the actual bounding boxes from the model, right? How do we actually finally take all those possible bounding boxes that the model spews out and get the few bounding boxes that we think are relevant to us, that are relevant to the image? So first thing we got to do is each box will have a associated confidence, right? The confidence is simply the loss function. So each bounding box will have a associated confidence. So we're just going to, ideally, the bounding boxes that the model is most confident in are the bounding boxes we should use, right? That's like the first thing, that each bounding box will have a certain confidence score, a certain loss for the model. So yeah, so that bounding box is the thing that we're going to use, okay? Certain confidence score. So the bounding box with the greatest confidence score. how do we, if we just take that one bounding box, I mean, what if two bounding boxes have are overlapping, right? What if we have one bounding box that has a really high confidence score of like 0.9, and we have another bounding box that has a low confidence, like a lower confidence score, like 0.5, but they're not overlapping. Like, are they segmenting the same thing? Are they bounding two different things? Those are things we need to consider, right? So, as far as how we do this, there are multiple different techniques, as always. I know you guys are getting tired of me hearing me say that, but multiple different techniques. But if we look at, the most important technique is what's called non-maximum suppression. Okay, so the idea behind non-maximum suppression is that we simply want to take the bounding box with the highest confidence and suppress the other bounding boxes that overlap it that have lower confidence scores. That's the thought process. Our thought process is that, you know, the bounding boxes that overlap this are probably identifying the same objects, especially if they have the same class, I should say. So if they have the same class and they're overlapping each other, then they're probably all bound, or at least attempting to bound the same object. So what we should do is find the box that has the highest confidence score. And then all we need to do is find the boxes that are overlapping with this box that have the same classification, and then just get rid of them. Right? So if we do that, it ends up working pretty well. It ends up, for instance, we have a box that is the actual one that we want with the dog. And then we have a bunch of other boxes that some of them are actually trying to bound the dog. There are other ones that aren't terrible, especially like the yellow one is the truth. So you have this green one here, this green one here. There are a lot of the other ones aren't terrible. They're not great, but they're not terrible. But they have lower confidence scores than this yellow one, right? So we just take the most confident bounding box, and then we look at all the other bounding boxes, overlapping it, and with the same classification, and just get rid of them. And if we do that, if we iterate through that, we'll hopefully be left with only the bounding boxes for the objects only the bounding boxes that actually bound the objects well. Or the bounding box that the model thinks best bounds the object. Okay? In another way, just to visualize that, this is just some code to visualize that. You have a bounding box, you have some of them that are overlapping, you have some of them that are not overlapping. You just take the ones that are, you just look to see which ones have the highest confidence score. So right here, this bounding box out here has the highest confidence score. Then you just get rid of the rest of the bounding boxes that overlap with it. And if the bounding boxes are not overlapping, then you just sort of let it go as well. Okay? So, is it perfect? No, it's not perfect because, you could always have objects that, if you have two dogs that are almost on top of each other, then it could lead to issues. But hopefully, even in that case, if you have two dogs that are very close together, either your classifications will be different, or, the bounding box, there could be two bounding boxes that are neighboring each other that way. And then you will have different confidence scores for that in that case. Does that make sense? Okay. So, non-maximum suppression, you'll see that, non-maximum suppression, you'll see that a lot. And then, as always, the last thing we need to determine is our accuracy metric. So not necessarily our loss function. Our loss function simply tries to train the model, right? But just a single numeric value doesn't mean a whole lot to us, especially in the case of image processing. So in the case of image processing, we could have something that's if there is something there, we could have something that, if there is something there, identifies that thing there very frequently. But it would also give us a whole bunch of false positives. Basically, it finds a lot of objects and it draws bounds behind a lot of objects, when in reality we just wanted all the pictures of dogs, you know? So we could have a situation that, you know, if we draw a bounding box with around every object, I mean, we're guaranteed to get we're guaranteed to get the objects we want, but we're also guaranteed to get the objects that we don't want. So in order to discriminate between that, we want to know how many of the objects that we retrieve are the actual objects we want. That's what's called precision. Okay? How many of the objects that the model outputs are actually objects that we want? That's the precision of the model. But then there's another aspect to this, which is, well, our false positive is so bad. Really, what we're more concerned with is finding all the true objects we want. If this is a picture of dogs, what if we are more concerned with finding all the picture of dogs rather than just finding some of the picture of dogs, right? So that's what's called recall. The idea that if you have a bunch of positive ground truths, that you retrieve all the positive ground truths. Okay? So you have these two sometimes competing measures of accuracy. If you have a ground truth, how likely are you to retrieve that ground truth? Or if you retrieve something, how likely is it to be a ground truth? These are two very different ideas, right? So this is just sort of a visual representation of these ideas. So what do we do in this case? Well, there are a lot of different metrics that go into this, but the idea is come on, there we go. Oh, there we go. There are multiple different there are multiple different aspects that go into this, but we need to determine. There are multiple different aspects that go into this, but we have but we have this issue right now, which is the more stuff our model outputs, the higher our recall will go, but also the lower our precision will be, right? The more results we retrieve from our model, basically, the more results we retrieve from our model, the more likelihood we are to get the ground truths, all the ground truths. That's true. So our recall will go bigger, but our precision will go smaller because the more results we retrieve, the more likelihood that we are to retrieve a negative ground truth, right? So when we have these two competing metrics, I mean, the thing that we could best do is simply to create a graph. Okay? So what do we do with this graph? I'm going to make it a little bigger. There we go. So what do we do with this graph? Well, again, we have our model that can output 100 different bounding boxes. I mean, it's just guessing, right? The model doesn't really know what's a ground truth. The model doesn't know what's a dog. It's just like, you know, if I have to pick something, I'm going to pick this, right? So it outputs 1,000 different picks. And then we suppress a lot of those picks using maximum suppression. So we have more of those picks. But again, even after we run maximum suppression, some of those bounding boxes are going to be more confident than others. So we could tell ourselves, we could set a threshold. We will only accept bounding boxes with a confidence score of 0.5 or higher. Well, that's fine. Or we could just go down the list. We could go down the list and accept all of those bounding boxes. But we want to measure the bounding boxes with the highest confidence. We want to measure how accurate they are more than the bounding boxes with the lowest confidence. Okay? So what we'll do is we'll order all the bounding boxes. We'll rank them according to their confidence, according to the confidence that the model gives. And then if the model is true, then we'll adjust the precision and we'll adjust the recall. Okay? So for instance, if there is simply one bounding box, and in this case, so like suppose we have a model and the image contains 5 apples and we need to detect all 5 of those apples, right? So what we do is, for instance, if we go with the top result, the bounding box the model is most confident in, the precision will be 1 because it has one bounding box, and that bounding box is a ground truth, right? And we're going to assume that we say that bounding box is positive if the intersection over union is above a certain threshold, in this case 0.5. Okay? So we're going to say so if we get that out of bounding box, then we're like, okay, this overlaps with the ground truth bounding box, at least half of it does. Then we're going to calculate our precision, which will be 1 because we've only retrieved 1 bounding box and it's a truth. And then we're going to calculate a recall, which is 0.2 because there are 5 ground truths and we only retrieved 1 so far. Similarly, we take the next one, right? The next one, our precision will be 1, and then our recall will be 0.4 because we calculated bounding box. Because both of the bounding boxes we got are ground truth, so they're both precision. The precision will be 1, and the recall will be 0.4 because we retrieved 2 of the 5 apples in the image, right? And then if we, for instance, the third bounding box we get that the model is very confident in, not as confident as 1 or 2, but it's still very confident in this bounding box. But it turns out this bounding box doesn't overlap with a ground truth bounding box, at least not by enough. Well, then our precision goes down because that counts as a false positive. And our recall stays the same because while we retrieved another bounding box, it wasn't a true bounding box. So again, recall is simply a measure of the number of ground truths we have retrieved over the total number of ground truths. Okay? So if we plot this, okay, so we could go down all of these values and we could actually plot this. Okay, if we plot this, we could plot this on a curve. This is called the precision recall curve. And so if we plot this on a precision recall curve, we see that, depending on the recall, we either get a higher precision. The general trend is the lower the recall, the higher precision. That makes sense. So we have this curve. And so the metric that most people use is called mean average precision. Okay? So the mean average precision is simply the area under this curve. Okay? So if our model is absolutely perfect, if, for instance, the model, the first 5 values are all 1 and 1, then this would, like the first values are, then basically at every value of the recall, we would have a 1. And then, what would we do in this case? And then the mean average precision, the area under this curve would simply be 1. Okay? But if, for instance, our precision greatly decreases as our recall increases, then what does this tell us? This tells us that as we get more values, as we get more values, the more values we get, the less likely those values are to be related to a ground truth. And so that means that, so the area under that curve will be much smaller. So the map, the mean average precision score would be smaller. Okay? So the mean average precision is a way to relate these two values into a single metric. Okay? And this is how most image models are evaluated. This one metric called the map score. And there's a lot of nuance with this. This curve is often normalized, so very often times you take the maximum values at any point in the iteration, or you normalize it to, normalize it to eliminate the zigzags. The map score in general has a bunch of different variations. I think, has anyone dealt with information retrieval? No? Okay. So there is a this map score comes up in information retrieval a lot. And basically, you will see this if you look at IR papers, you will see something to the effect of map at 10, map at 20. And so map at 10 simply means of the first 10 retrieved results, then which of those results are relevant toward a query, which of those results are not relevant toward a query, and then you calculate the map score that way. You can see the analog here. So this is a very IR thing, but it's also there's a lot of image specific. The COCO evaluation is image specific, and the COCO evaluation actually averages the mean average precision over multiple intersection over union values. This was for only one intersection over union value. You could imagine if, for instance, I adjusted this threshold to be like 0.1, then maybe the recall would go up, the precision would go up. If I adjusted this threshold higher, like 0.9, you could imagine this curve will be even smaller. Okay, so multiple different aspects. Your vision project topic contains code to calculate the map score. So it's important you know what it is. Okay. All right. So. Last stretch, multiple little things that I'll just run through. As we saw before, we saw with our bounding box model that you had that sort of grid, that you had those sort of grid anchors. One issue with that model is if you use a fixed grid, it makes detecting bounding boxes of different sizes more difficult. So modern image models typically have multiple what's called heads of different resolutions. So each of these heads outputs different bounding boxes, and then you run through the same, maximal suppression, non-max suppression, and all of that other good stuff to get the bounding boxes of different sizes. That's just one thing that this is one of those things in practice that you need to fix. Yeah, and then last thing I want to put out there is that the whole point, a lot of this is, a lot of encoder-decoder models are especially important because of transfer learning. Transfer learning is the idea that you could train a model on one task and then use information gained from that task on another task. So for instance, with the segmentation class or with the classification task, we could train a image model where we have an encoder, and then we have a decoder that takes the features at the end of this encoder and then converts it to some n-dimensional vector, right? So the nice little thing is that, we could take this model. This is if we do this for one or more tasks, if we do this training for one or more tasks, this model here, this encoder here, becomes a pre-trained model. And so having a pre-trained model, is useful because, again, we don't all have the resources of Google to train a model on millions of images, probably billions of images. So what, Google or what large language models do is that, what these big companies do is that they train their models on a bunch of different tasks. And so we get these encoders, and then they release these encoders online. So what we do is we freeze the weights of these encoders, we attach a network to their outputs, and then we adjust the decoder for a specific task. Okay? So this is probably what you're going to end up doing for your project. Again, that's why we have the parameter limit, is because, you know, a lot of you are going to go online. PyTorch has a lot of default models, default image models that were trained on very large image data sets, much larger than we could do on our own. So the smart thing to do would be to simply get those pre-trained models, load them into PyTorch, and then attach augment them however you need to output whatever you need to output, okay? So this is the idea behind encoder-decoder models. We're going to talk more about encoder-decoder architecture in the context of NLP, in the context of language modeling on Thursday. So Thursday, we're going to discuss transformers and begin to discuss LMs. And as far as the project is done, the Kaggle infrastructure is done. We're just updating the general topic pages, and we'll release it. We'll release updates on how to submit models to Kaggle later this week. So stay tuned for that. Okay. Any questions? All right. Thanks, guys, for coming, and I'll see you Thursday.